At Mecca. Mecca, how are you?
Good morning, everyone. Um, I welcome you to the fifth day of the summer school, and today we'll be discussing observational astronomy. The course will be taken by two instructors, Professor James Chibeze and Dr. Masirat Soge. This first session will be taken by Professor James, and Professor James is a professor of astronomy at the University of South Africa. He's also currently the Vice President of International Astronomical Union. Prof, over to you.
Okay, good morning, everyone. Can you hear me clearly?
Loud and clear.
Okay, so I'll recommend, I can hear some feedback. Probably if you're not talking, the best idea will be to mute yourself. And then I'd like to make a small request. I know this might be a bit hectic for the students or the participants. I would like to move the break to between my lecture and Dr. Shoge's lecture because I have to run to a FAST science committee meeting. So I'll run through my first part of my lecture, which will cover optical astronomy. And then I'll go to radio astronomy, which is actually my specialty. And then I'll give you time to rest. And then Dr. Shoge will show you something on spectroscopy. Is that acceptable for everyone?
Okay, I think since there is no alternative, maybe we can accept it. But ordinarily, we would have loved to have it the usual way. But we can accept it that way. Go ahead with the presentation.
Yes, I can show you my screen that I have two concurrent. You can see my screen, right? You will see this
Yes.
meeting reminder. This is a meeting happening just at the same time as this lecture, and then the FAST conference, FAST Science Committee meeting starts in about 58 minutes. But I've told them to go ahead. I'll join them maybe 30 minutes late.
Okay. You can
Yeah.
adjust the break period.
Okay,
Thank
please.
you. Yeah.
That's my plight. Okay, cool. So, but don't worry, I'll try as much as possible to do justice to this. I can't see your faces, but please unmute yourself if you have any question in between. It's better you understand it than I cover much material and you understand nothing. Okay, so feel free to unmute, and ask questions. I'm trying to minimize this thing. Okay, cool. Maybe I should also just take out the video just in case there are people who have limited bandwidth. So I'll stop my video. If you want to see my face, scream anytime, I'll put it back on. Cool. Now back to business. If you stop hearing me, let me know. Chifodo, you can WhatsApp me. So I'll tell you about optical astronomy, how it is done, how the telescopes work, and what CCD camera is all about. I'm sure you've heard CCD, but I'll show you the operational mechanism today. Typically, in the major kind of astronomy most of you know is the optical astronomy, because you most likely have seen an optical telescope at one point in your life or the other. If you haven't, please endeavor to find one and look through it to observe any object in the universe, maybe the moon, which is one of the nearest astronomical objects. But essentially, what the telescope does is to just collect light. In this case, optical light. Be careful. Sometimes we use lights to refer to invisible light, which is in the radio band or in the other higher frequency band, which you cannot see. But we're focusing on optical. So an optical telescope will collect all the light and focus it in one point to make an image of the object that is either reflecting the light or emitting the light. I've mentioned two things. The object could be emitting the light. For example, the case of the sun produces light out of itself. So the light you see if you look through maybe a well-filtered telescope to look at the sun, is emitted by the sun. But if you look at the moon doesn't have the capacity to emit light. So every light you see from the moon is a light that the moon has reflected from the sun. There are two types of optical telescopes. You can have a reflecting telescope. You can also have a refracting telescope. And this is all used in different ways in all wave bands that we do astronomy in, which covers all electromagnetic spectrum. Cool. So, of course, the telescope will focus the light, but then you need something that is sensitive to light to be able to detect the charges or the optical photons. I do hope you know what photons are. Photons are quantum mechanical system that describes something that can behave as a wave sometimes or sometimes as a particle. Cool. So you need a telescope, but you also need a sensor to detect the light. And in optical astronomy, and of course in infrared and some part of UV, we use what we call the charge coupled device, the CCD system, to detect the light photons. I'll explain the procedure later on. CCDs are simply pixelated devices made from silicon. And of course, I said pixelated. It means they have pixels and they can convert the optical photon into electrons. Well, that is not conversion. It simply means that the photons have sufficient energy to knock out an electron in silicon and make it move from the valence band to the conduction band. I will show that again much later. So your angular resolution is limited to the size of your pixel. So if your pixel is very, very small, then you have very high angular resolution. It means you can see finer details in your observation. If the total area of all the pixels that you have, of course, you can have small size pixel, but if you have a lot of them, then it will make a huge area, because small pixels times, say, 2 billion pixels is a huge area, and that gives you the coverage you have in the sky when you point your telescope and capture the image with that CCD. In this case, CCD device. In this case, we call it camera. So this is an illustration of what a CCD device looks like. I can't see my cursor, but I hope you can see it. You'll see things that have vertical and horizontal wells, tiny blocks, okay? The smallest block in the brown block region you're seeing is 1 pixel in this CCD device. But before we go into really complicated things, it will be very important to show you that telescopes work on basic physics principles. You do know the principle of reflection of a wave. If you take a plane wave and put a reflector of the plane wave, what you will find is that the incident angle, in this case theta in, will be equal to the reflected angle, or the angle of reflection, which you call in this diagram theta out. The measurement of these angles is not from the reflection point. It's typically from what we call a normal, which is a line that is perpendicular to the surface that is reflecting the waves. And basic reflection principle says theta in will be equal to theta out. And for reflecting reflector telescopes, it's easier to make them with spherical profiles. And the way you do this, now I'll need to switch on my camera. Okay. Okay, I do hope you can see me now. But the way you make this, if you cannot see me, please scream. If this is a lens or a mirror or anything, okay? And this is another one. And the top one is concave in shape. And you put it on a second one and grind, okay? Typically, you have a bit of water so you don't break the glass, but you just keep grinding it for a long time. This is now automated process since we have improved technology. But before now, it was done by hand. The first few optical telescopes that were built in the 1900s were all done manually. Put glass on each other and then grind until you get the shape that you want. But now we do this with machineries. So you can generate through grinding, the top part will give you a concave shape, and then the bottom part produces a convex sphere. I'm saying this on the assumption that you do have some fundamental optics, physics module course that you've taken, and you understand what concave and convex means. So spherical mirrors, remember that the optical telescope is aimed at focusing all the optical lights reflecting on the surface of the mirror to one point. So the original kind of mirrors that were built many years ago were spherical mirrors. And you take in a concave mirror, put it on the top, and then you grind against another mirror, but on the bottom, you produce a convex mirror at the bottom. But this has a huge disadvantage. If you've read a few documentaries about the Hubble Space Telescope, which was originally a spherical mirror, you will understand that this is one of the problems that plagued the Hubble Space Telescope. For concave spherical mirrors, they're typically very bad at doing imaging for stars, even within our galaxy. The reason is because of what you call spherical aberration. I'm sure you've seen this, but you just did not know what it was. Sometimes you take a photo of an object and you notice that the different colors in the photo are all shifted by small offsets from each other. When you see such thing, what you're experiencing is some kind of aberration, and in most cases is spherical aberration. And that is because the light coming from a distance and striking the surface of the spherical mirror, okay, it's not focused at one point, as you can see in this instant. The red lines are light coming from a distance. The white arc is the spherical mirror. And under normal circumstances, for you to make a good image that is not affected by aberration, all the reflected light, okay, bouncing on the surface should all converge at one point. So the fact that it lacks convergence means that lights, well, if we say lights, you're talking about multiple color lights, okay, that come together to form the white light you see. Now, that split is separating multiple wavelengths within the optical band and putting them at different focal points. And therefore, you will see the same image in red as in blue, but it will not match one-on-one. There will be a small shift in the image. So this was one of the problems Hubble telescope had, and that's why we had to send people in space to fix it. To fix the problem, you just need to shift from building something that is spherical. I do hope that, remember, the lecture time is very, very short. I did complain to the organizers that 2 hours is insufficient, but it would be good for you to go back to your basic mathematics, write equation of a sphere, okay? And you can cut half of the radius of the sphere. You draw a radius of a sphere, you cut out half of that radius, and you take that arc. Now you can do the same with a parabola, write the equation of a parabola, maybe make a figure of it, and then cut out a small fraction of the parabola. You will realize that the arc of a parabola, as is shown here in the brown line, or the brown arc, is it's more relaxed in the curves and therefore easier to focus all the rays. It corrects the defects you see when you use a spherical mirror. And you can see in this case, all the reflecting rays are all reflected and focused at the point. So parabolic mirrors are now very popular. In fact, in radio astronomy, I will show you later on, we also use parabolic dishes because it's easy to get a focal point. Any questions so far? Any? Unmute yourself. I cannot see anything on my screen. If you're raising your hand, I'll be able
We
to see
don't
it.
see any raised hand. I don't see any raised hand.
All right, cool. So I'll move on. So there are basic designs to that you could have for optical telescopes. You could have things that are what we call prime focus, where the light is brought in focus by a primary mirror only. Okay, you don't need a secondary mirror to reflect anything. But if you have a Newtonian telescope, you may have had Newtonian, Cassegrain, Naismith. Those are different kinds of configurations that you could use in building telescope. We also use that in radio as well. So typically these Newtonians are typically flat. They have a bit diagonal secondary mirror that will reflect the light out of the tube. You've seen this. If you've seen a telescope, there is the main mirror that converges light here. And this light that is converged here, you put a reflector here, okay? So if you send light directly at horizontal and place an inverted 45 degrees, this is going to make the light bend 90 degrees. So the secondary mirror is usually just used to deflect the light so that the tube is pointing to the source, but you, the observer, is looking perpendicular to the direction of the main tube pointing to the light source. Okay, so the Cassegrain typically will have a convex secondary mirror, and that reflects light through the hole in a primary mirror. And the Naismith typically have a tertiary mirror. Naismith is used in situation where you are taking care of real estate. Real estate, when I use that word, I just mean space, okay? If you want people to sit in this room and observe with a telescope that is outside, you might need to bend the light multiple times before it gets into the room, okay? Just helping it travel the distance. So Naismith is one example of that. Again, this is used in, I probably will show you examples in radio astronomy when I give that course. If I assume everyone is happy, I'll start defining some parameters and showing you what they mean. The first one being what we call the plate scale and the F ratio. So F ratio is typically defined as F hash and is equal to the focal length of your lens or your mirror divided by the diameter of the mirror. Cool. So if you have that value, then I'll give you a definition of plate scale, okay? And then you would see how we put that together because it's very easy to define plate scale in terms of F ratio. So plate scale is 1 over your focal length, okay? So if you take plate scale as 1 over the focal length, then 1 over focal length is actually F ratio multiplied by the diameter of your dish. So 1 over that is just 1 over F ratio multiplied by the diameter. Does that make sense?
Okay.
No answer?
No response. Maybe okay, yes, on the chats. Yes, they are already replying.
Okay. Cool. Now, to put that out with an example, if you put out the plate scale, which is theta over s, don't worry, I'll hope you would have a look at this and understand theta over s much clearer. Then you can define that as 1 over plate scale multiplied by diameter. So if you have a 10-inch telescope with f over 16 focal point, then you can calculate that. F over 16 just tells you what the F ratio is. It means the focal length divided by 16, right? So that's the F ratio. So if you have that, then it's actually the F ratio is 16, and then the diameter, which is 10 inches. 10 inches is equivalent to 254 millimeters, and you can determine the plate scale, which will be that your plate scale will give you 2.5 times 10 to the power minus 4 arc seconds per millimeter. Okay. Cool. So with those definitions, I'd like to show you things about the sensors and, of course, what we mean by pixels and how those are defined. The eye is the first and the most famous optical telescope. Your eye has got a light-sensitive component, which is about 1 millimeter in diameter. I think it's called the pupil. That is sensitive to light. It picks up light, okay? I don't think it has silicon, but somehow is able to detect light, okay? In telescopes, you can converge the light. The reason we build telescope is that we want to pull the light in as many as possible, as much as the photons as possible, converge it to one point, and send it to a sensor. What are these sensors? They're simply charge-coupled device. What does it mean to have a charge-coupled device? Well, it simply means you have a device that when you incident a photon that has an energy equivalent to the energy of optical light, you'll be wondering, why do I say optical light has energy? Energy is Planck's constant multiplied by frequency, all right? So you can always change frequency with speed of light to wavelength. So if you determine the wavelength, the photon optical light will have is just the energy that a photon can carry when it has wavelength in the range of optical light frequency in the EM spectrum. So such photon would be able to knock out electron from silicon, as I will show later on, and that electron with some electric field applied will be prevented from recombining with a proton and becoming or recombining with the positively charged atom where it was knocked out from. And so it doesn't become neutral anymore. So you are able to keep it separate and count the electrons that has been knocked out. Okay, so pixels within CCD camera just helps you read out the sequence to show you in this region, there are more photons arriving than in that region. So you look at an object observed in optical and you see some parts are brighter and the other parts are less bright than others. So that's just depending on the number of photons knocking out electron in those pixels. However, you saw when I showed you a photo of a pixel of a CCD camera or CCD device earlier, that the pixels are fairly ordered. Like if it's 10 by 10, then there is number 1, 2, 3 to maybe 10, and then 1 to 10, 1 to 10, just like that. You cannot randomly pick the pixels wherever you want and place them however you want. It has to be done in an orderly manner. Okay, so I've posted this online just for you to use plate scale to determine what your pixel size is. Remember, your pixel is just tiny, sometimes 1 millimeter or 2 millimeter or less than a millimeter by a millimeter size area within your CCD. So you can calculate like is shown here with your pixel scale to show that 1 pixel is probably 1 arc second or 2 arc second or 3 arc second, depending on the size of your camera per pixel. Why is that important? Well, whatever the size of your pixel is, that is the smallest size, and that is your angular resolution. Okay. That gives information about the finest detail you can resolve in any object you observe in the sky with that CCD camera. Okay, the field of view. 1 pixel tells you the size you can observe. 1 pixel times the total number of pixels gives you the area in the sky you can cover. Okay, when I say the total number, remember if I say you use cameras on your phone, maybe your phone is 6 megapixels, it just means 6 million pixels. And you have to find the square root of 6 to find what one axis is, right? Okay, so the field of view is going to be the size of 1 pixel in angle multiplied by 1 dimension of your pixel. Okay. In this case, it's 1 million, and 1 dimension of it is going to be 1,000. And therefore, the field of a telescope, the field of view of a telescope that has pixels that are 1.2 arc seconds, you just need to multiply by 1,000. And that is 1,250 arc seconds. You divide that by 60, that's equivalent to about 21 arc minutes. Here it says it could image most of moon's surface on this through this telescope. Most just indicates it's not all, because the moon is about 30 arc minutes in size. So you need a field of view. A field of view is an area when you point your telescope, an area you can cover at once. Okay, in this case, it's 21 arc minutes. Any questions so far?
Aman, go ahead with your question.
My question is, what happens if you multiply 1 over focal length by the equation to find focal ratio? What answer will you get?
When you multiply?
1 over focal length times the equation you get to get focal ratio. What answer will you get?
I don't understand what you mean.
I
Which of
also
the
didn't
equations
get
are
the
you,
question.
which of the equations are you referring to?
The previous slide.
This one?
No, before that.
This?
Yeah, this one is this one. 1 over focal length equals like 1 over focal ratio times diameter. So what I'm asking is how do you just single out to get focal length? Like you said, 1 over focal length equals 1 over focal ratio times diameter. So how would you find the focal length?
Yeah, focal length is just F ratio multiplied by diameter, right?
And that's how you get your answer.
Yes.
Oh, so you just ignore the one at the top.
Well, if you divide anything by 1, it stays the same. If you multiply anything by 1, it stays the same.
Okay. Thank you, Professor.
All right. Okay, thanks. Okay, everything here is something that I have described earlier. However, there is something we call blurring of image, which is caused by diffraction limits of your instrument. Okay, so how do I explain? So the diffraction limits of your telescope is one factor that you typically would consider. Maybe for time, I would recommend that you have a look at what diffraction limits are. Of course, there are other things, things that like in optical, like what we call seeing. And seeing is can affect actually your angular resolution. And that is as a result of random fluctuation in the atmosphere. So the thickness of gas, not only water molecular cloud, the thickness of different kinds of gas in the atmosphere can reduce your seeing, which is just how much detail you can see of an object in the sky. And that could cause blurring. So you hear optical astronomers talk about going for observation and having poor seeing, and maybe the seeing was not good enough to observe the source they are interested in. So what are the basic principles of getting images from CCD cameras? That's what I'll explain to you next. How would you move from taking your tube? The telescope itself is just a tube that contains a mirror. Okay, it could be, well, if you're using a refracting telescope, it will contain lens, but in most cases, good telescopes are now mostly mirrors. And how do you move from that to this kind of image? This is probably an image that many of you know quite well, an astronomical image. Just first, a bit of history. CCD is charge-coupled device, invented in the 1970s, originally just as a memory device for doing mathematics. And most of it, even until now, are made of silicon, and they are very sensitive to light. And I'll show you some calculation on why this is sensitive to optical photons. For CCD cameras, you always can characterize them and reproduce a map that show what the sensitivities to different bands are. For example, if you take a silicon-made CCD camera and expose it to light from, say, 300 to about 1,000 nanometers, this is the wavelength of the light, you would see that at UV, yes, it does pick up some emission. You will see it's quite low. Well, actually at 300 is almost nothing, but quite low. But it starts rising and rise in the UV band up to 400 nanometers. But in the visible band, you know, the visible is made up of light from red to violet. Okay, you can go find what is in between, and CCDs are fairly sensitive to all that, because the sensitivity drops as you go move lower in the wavelengths. Then in the infrared, if you are in the near infrared, then you're very good. If you go towards far infrared, CCD starts to fail you. Now, if you look at the infrared band where things drop, like in 1,000 nanometers, where things drop that you can no longer use CCDs, that is the regime where you start to see people observing with radio telescopes at millimeter wavelengths. Okay, so that's the response, the spectral response of a typical CCD camera. I already said it's light sensitive, well, can be powerful, and was used in the past to, do lots of observations. And before CCDs were developed, there was things like photographic plates and films. You probably, maybe many of the students will not have seen a film. Before now, we never took, before cell phone came up, we never took photos and saw it immediately. You take a photo, you wait for the film to be developed, and then things get printed. So those thin films where images were captured were sensitive to light, but you needed additional processing to be able to get the image. If you go to old observatories, you still find historic photographic plates on which some of these lights were recorded. But we don't do that anymore. We capture these images in real time. However, photographic plates are still very useful. I recommend you look for one of them if you can in any observatory and take a look. One, they are very cheap. Two, they can allow you record a very wide field of view image on the plate. So those are still extremely useful. In fact, data storage with tapes or thin films are still more efficient than storing things in your current SSD drives because they are quite volatile. Okay. CCDs are made of silicon. I've said that before. And that is only possible because silicon show a crystal structure, okay? And silicon has this nice morphology that, or nice structures and good arrangement of the electrons that enables incoming photon to be able to knock out an electron from silicon. Of course, initially people could just count this in analog form, but these measurements are now pixelated and digitized and stored in computer files. Here's what silicon looks like. Okay, if you take an electron microscope and pick a piece of sand on the ground, it will be dominantly silicon. There might be a few oxides in the sand, but much of the sand you see on the ground is made up of silicon. Now, if you take that and look through electron microscope and you can see subatomic levels, that's the morphology, that's the arrangement of the particles. The lines there you will not see. You won't see the bonds holding this, but you will see that the particles or the electrons in this are nicely arranged in a beautiful pattern of structure. Now, if you use this silicon atom, and of course, many other silicon atoms to build a CCD camera, what you are doing is simply taking these well-arranged structures and putting them in devices. If you bring in optical light and hit this, you will excite an electron to move away from where it was originally bonded and fly into what we call the conduction band. What does that mean? It means, all the available states in this crystal structure is arranged in discrete energy levels, okay? The lower energy level, which is the stable state, is called the valence band. Those have much more electrons. Typically, you find nothing in a neutral system. You find nothing in the conduction band, which is a higher energy level, okay? They will typically have no or fewer electrons. Now, there is no state between the valence bond and the conduction bond. The band in where you call the conduction band has a gap between it, and there is no intermediary state in it. Now, how much energy does it take an electron to move between valence band and conduction band? That is, in the case of silicon, equivalent to 1.26 electron volts. So if you can inject a photon carrying an energy that is equal to or greater than 1.26 electron volts, then that photon will be able to knock an electron and inject that energy into an electron, and then it will jump to higher energy level and get into the conduction band. If you leave things in that state where there is a free electron in the conduction band, of course, that means there is a free positively charged particle in the valence band, then those two could recombine and become neutral again, okay? So as I mentioned earlier in CCD, the idea is always to inject an electric field, okay? If you inject the electric field, it's just injecting electrons so that it will pull apart the positive and negative charge to keep them separated so they don't recombine. But first, why is this energy necessary? Well, I have said the incoming photon definitely need the minimum energy to knock out an electron of 1.26 electron volts. In the conduction band, the electron is free to move around, and you make sure that things don't recombine. Okay. The positively charged particle we typically call a hole. It's called a hole because if you allow it, it's going to sink the electron again and become neutral. Okay. Any questions so far? Cool.
No raised hand. Okay, Inyama, go ahead.
All right, thank you, Professor. So I want to ask if there is any work being done in regard to other materials, because I'm seeing the conduction, what do you call it again? The gap, the energy gap of silicon is 1.2, and so which means other photons will be transmitted of lower energy, and even those of higher energy won't be absorbed to move the electron from the valence band to the conduction band. So are there other materials that are used to capture the other photons with other energy?
Beautiful question. I will suspect the chemists are all in terms of the energies you need to knock out electron from different kinds of atoms, you can already calculate this. So the chemists are producing those kind of calculations and releasing the result. But in practice, it's mostly silicon that we use for this. There are people trying to make alloys of silicon to see if they can lower the energies of the conduction band. Remember, if you lower the energies of the conduction band, what it means is that we can now almost look at every band in the UV. And no. We can look at millimeter observation, which is now almost in the radio rim with silicon. So we can directly detect photons from millimeter waves emission. So yeah, there is effort towards doing that, but at least in the current technology, what we have is only silicon.
Thank you, Prof.
Okay. Cool. So in optical astronomy, if you take photo with your cell phone, which is the same as optical astronomy, you are essentially capturing and counting photons with those your devices. Why do we need a specific wavelength to be able, well, specific energy to do this? Remember, I've shown earlier that you need 1.26 electron volts, and you can walk things backward. Okay, I've said energy is h nu. If you go to this equation that says lambda equals hc over E, it simply means E is equal to h nu. Nu is frequency, and frequency is essentially speed of light divided by wavelength, right? So you can derive the wavelength. And then you plug in 1 electron volt in X, in joules. And then, of course, we know what the speed of light is. We know what Planck's constant is. Then you would see that the wavelength, okay, the minimum wavelength you need is about 984 nanometers. Okay. If any photon, remember, photon behaves like a particle carrying energy and can behave as a wave. In the waveform, the wavelength must be less than 984 nanometers in order to be able to knock out electron from silicon. So if you have something that is longer than this value in wavelength, okay, 1 nanometer is 1 micron. Well, 984 nanometers, which is close to 1000 nanometer, is equal to 1 micron. So you are teetering around millimeter, sub-millimeter regime, okay? Okay. So that's why I say if you make better alloys, we can directly image 1 micron, what we currently call millimeter radio waves. So it cannot be longer. If it gets longer than that, then silicon becomes completely transparent. You make phone calls, okay? The walls you are in is made of sand. It's a lot of silicon in the walls. But if you sit in that room and I dial your phone, you cover yourself with all concrete all around, you still receive the phone call because the silicon cannot either reflect back or absorb those energies. They are completely transparent to energies lower than that energy. Okay, cool. So longer wavelength, transparency, anything shorter than 1 micron will be definitely absorbed. Sorry. Anything greater than 1 micron would not be, okay? Because it wouldn't have enough energy to kick electron to the conduction band, and therefore it becomes transparent. This is essentially the reason why radio astronomy is difficult, because in radio, we cannot directly count our photons. We cannot just capture image and then we print and then show nice fancy pictures like we do in optical. Okay, I'm nearing 45 minutes. I would like to speed up a bit, but I've uploaded this. I will provide my email address in the chat. You can always email me if you have questions. So I have explained this slide already. I said electron and positively charged particles quickly recombines. So usually you want to prevent that by inserting an external electric field to keep them separate. Okay, and then you're able to count the electrons that are knocked out. So this is what happens. You bring in a photon, you knock out an electron, and you leave a positively charged in the valence band, and the negatively charged run into the conduction band, and you try to insert electric field to separate these two, to keep them separated, and you find a way to count the photons. That's in principle what you're doing with your cell phone if you don't know. Okay. Cool. There is always problems when you do astronomy of any kind. You are interested in counting electrons that are knocked out from the silicon in your CCD. However, the CCD device itself works with power supply. And you do know that if you plug even your cell phone on power and you touch it, sometimes it gets warmer. Whatever is heating up the phone is associated with the motion of electrons, okay? That comes from the electronic systems, the transmitters or the receivers or the diodes or whatever you have in the system. So that warms up your cell phone. Warming up is just what you call ohmic loss. If you remember Ohm's law, if you pass current through any material that offers resistance, over time that material will start to heat up. Okay, that's ohmic losses. So that generates electrons. We call those thermally generated electrons. And those electrons can leak into your CCD camera and you would disguise as being electrons coming from silicon, and that will contribute noise. We call that thermal noise. The way you can mitigate against this is to cool your CCD camera. So in most sophisticated telescopes, the CCD cameras are put inside what we call cryogenic cooling system. I can explain that. It's like putting a box. If you take your phone and plug it and you're making phone call, it warms up. If you don't want the heat to continue, you can continue the phone call, but put your phone inside a deep freezer. So every heat coming from the operation of the telescope will be absorbed by the cold environment inside the deep freezer. So what we do is to build a chamber. We take compressed helium. If you compress helium, it will cool down. If you expand it, it will warm up through heat exchange with the environment. So we use that to extract the heat from the operation of the CCD cameras. And that can minimize your thermal noise. Good. Next, I'll answer a simple question. How do we count the charges? I have said before, you don't do this randomly, right? You don't take pixel number 32 and put anywhere you like and take pixel number 90 and put anywhere you like. No, this has to be counted sequentially because each one of them is capturing image from the sky that directly strikes the position of each pixel.
Somebody has a question.
Yes, please.
Edina, go ahead.
Yes, okay. I needed to ask this before it disappeared. So there's something I'm not getting here. You're
Yes.
saying that okay, you cool down your CCD so that you're not getting this disguised electrons, right? So
Yes.
from the physics I know is that something can be excited only by energy, and that energy would probably be heat. So you're talking about the photon striking the silicon, so that okay, after it strikes the silicon, you do you count? Okay, maybe you can just please repeat that part so that I
Yes.
understand well, because
No,
I don't
no
know if you're
problem.
getting what I'm trying to get
Yes,
to
I get
here.
it. Good. So your question is essentially, where does this other electron come from and why do they interfere, right? Isn't it?
No, like my question is, how do you now? How are you able now to count the real electrons when they're not even excited for them to to come off the silicon after being heated, after traveling from whatever the source to the silicon?
Okay, what is traveling from the source is not electron. What is traveling from the source is what's in quantum mechanics you call wave packets. It's a quantum mechanical concept that says that this thing can exist as a particle carrying energy, which means it can strike something and transfer the energy to that thing. It can also exist as a wave, which has a wavelength, right? Have you heard that before?
Yes, yes.
Okay, good. Optical photon can only have wavelengths. When we say wavelengths, we are now talking about the wave behavior of the optical photon of a certain range. If it's within that range, then it can hit, strike, in this case, acting like a particle, strike a silicon atom, and then knock out one electron. Now, in electricity, if you've done electricity in your undergraduate, electricity is just the flow of electrons through a media, right?
Yeah.
Okay. Now, for your CCD to function, you need to plug it to power supply. So there is electron flowing through a copper cable.
Yeah.
Now, if you operate any electronic device, because copper itself does not have 100% conductivity, so it has some resistivity value. There's a resistance value to copper. It means that Ohm's law will come into effect, right? Are you still?
Yeah. Yes. Yes. Yes.
Okay, so if Ohm's law kicks in, temperature will rise, right? Temperature rise is equivalent to some electron escaping from your entire circuit. Okay, those electrons are not electrons that have escaped from photons hitting silicon. This is electrons that come from your electronic device, the CCD camera itself. Now, sometimes that electron finds its way into your CCD system and is counted as electron coming from the silicon that has been, well, electron that has been knocked off from the silicon.
Okay.
And that is noise. It's not real electron you are interested in. It's something external. It's not part of something that comes from space. Then it contributes noise to your system.
Okay, thank you. Yeah, understood clearly. Thank you.
All right. Good. Feel free to ask again if there's something you don't understand.
Thank you.
Cool. So how do you count? Not randomly. You count in form of what we call bucket brigade. Don't worry, this is just an analogy to explain that you count things sequentially because you want to make sure that the number of electrons counted from one pixel is put in that pixel. Okay. Cool. So first, you open up your shutter. Okay. Everything you see here that looks like a cup is 1 pixel. So the pixel is lined up like you saw in the diagram I showed earlier. And then you open the shutter of your telescope and it rains photons. Okay. These are photons from the source that you're pointing the telescope at. It fills up. If it's brighter in the middle, the cups in the middle will fill up faster. If it's brighter at the edge, the cups at the edge will receive more photons than the other ones. So you have this conveyor belt is just to explain how you will sequentially count the electrons in each of the cups. And then you have this other measuring cylinder that you transfer the content of each cup into, and then you count. So when you finish, let's say you want to do 10 minutes integration on Orion, you all know Orion, which is in the, yeah, you can see it from the sky, I think now. You've captured it for 30 seconds. Then you close the shutter. Now, each of these cups or buckets contain different quantities of electrons in them. So what you do next is you empty it into the conveyor belt. And from the conveyor belt, this is transferred. So when you empty the first roll, you take things in the second roll and empty in the first one that is now empty. You take things in the third and empty into the second, and then later into the first, and you sequentially count them, okay? That way, for each bucket that is emptied in the measuring cylinder, you know you are counting, you know where exactly in the pixel it came from. Does it make sense?
Yes, it does.
Okay, good. So that's the principle, okay? So when you're done moving things, you empty into the measuring bucket, you measure, you drain, you put in the next one, you measure, you record, and then you drain. And that way you can go through the entire system and measure and record the values of all of them. So the number of electrons you count for each pixel is what you put in the image. Let me, oh, someone is drawing on my screen. Who's that? Okay, whoever is drawing that, can you please take that out? Okay, so if I go back to a sample image, if you split this supernova remnant into many pixels, you will realize that there is one pixel in the middle that is the brightest. Okay, that pixel, when it was counted, had more electrons, essentially. Okay, cool. Any questions?
I don't see any raised hand.
Okay, someone has drawn on my screen. I don't know who that is, but I don't know why it's allowed, but it's okay. You can ignore it. So as I have shown, the pixels are counted in sequence. The number of electrons in 1 pixels are measured one at a time so that you can record each value and read them out correctly. Okay. Cool. Sometimes there are problems, and some of you may have seen that in your images. I will show you example of, or cite some example of some bucket leakage problem you could have. Bucket leakage could mean that either your bucket or your pixel is damaged, or that you had so much electrons that you fill up the pixel. The maximum number of electrons is of the order of 300,000 electrons per pixel. That's the maximum you can probably count. So here is, again, a more simpler structure of the pixel. You can see in the pink part of the figure, everything in the first row behind is loaded into the readout lane, and then the output or the output amplifier, that is where you take things out and count them, count the charges. Okay. Good, so you do it in sequence, and in that sequence you cannot, of course, this is a programmable system. You will not make mistakes in terms of writing the number of electrons in 1 pixel. Okay, that's what the real pixel looks like when you manufacture it. This is one of the fabricated CCDs that has 1,312 by 1,035 pixels. So remember, this is a zoomed in image. If this was in your phone, it's just equivalent to 1.3 or approximately 1.4 megapixels. So where does the noise come from? I've told you about thermal noise. Okay. So there is a noise type that we call the dark current. Dark current is things that are flowing inside your electrons that are detected by your CCD, but do not come from electrons knocked out of silicon. They come from your own system. So the way you calibrate that is you cover your telescope, okay? You don't expose your mirror, and then you take a photo. Okay? You capture data while not exposing your telescope. So that means that any electron you capture there is not coming from electron that has been knocked out from silicon, because there is no photon coming into the telescope. So every electron you capture is from the system, and that is dark current. There's also the readout noise. Sometimes the counting process, remember this is an electronic system, can have some Nyquist or Poisson errors. Yeah, so if you don't read out correctly, or if any pixel is damaged, reading out could be a problem and can introduce error. Photon counting have statistical error, which you can constrain with Poisson statistics. There are also times you will have one of your pixels damaged. I'm sure many of you have seen that, absolutely. If you use a broken camera in your phone to take a photo, part of the photo not affected will be good. Some parts will have maybe one black line or multiple black lines. So that patch of your pixel is now damaged, and therefore produces incomplete or bad image. There are many ways you can correct bad pixels. I can tell you one. If you have a camera on your phone and you take photo of somebody and one part of the face is bad, okay? So you can do what we call dithering. So you know that if you take the photo, this side is bad and this side is good. So you can shift your camera such that you take the first one, cover this side, and then you take a second one, shifting your camera so that the image of this side appear on the good side of your pixel. And then you combine the two images. Then you have a complete one. Of course, that's very difficult to do maybe with, it's not actually, with a cell phone is fairly easy. Okay, so detail your telescope and then you can fix problems of bad pixels. I would like to skip quickly. Well, saturation, I have mentioned. Quantum efficiency, I can talk about if it's important later. Saturation is just when you fill up the bucket. Okay, I've said the number of electrons that one bucket can take, but if you decide to expose your camera for a long time, then you could saturate some of the pixels where a lot of electrons are being kicked into.
We have one question on chat.
Yes, please.
What is the covering done with when trying to avoid dark current?
And when you want to take image you will use to correct for dark current.
Yeah.
If you see a telescope, it usually has a black colored, sometimes plastic, sometimes metallic, that you just need to use and plug on top of the tube of the telescope. So it's a shutter. It's like a cover for you. If you have a plate that has a cover, it's just like that cover, so that light doesn't come in. Okay. If you like, you can cover it with your black shirt. Light will not come in. Well, black shirt maybe not enough. Okay. Did I answer you correctly?
Yeah, he has acknowledged that. Thank you.
Okay. Cool. There's something you call blooming. I've said that CCD 1 pixel has finite number of electrons it can take, and it's up to 300,000. If you put more than 300,000, it's like filling your bucket of 20 liters with 30 liters of water, okay? 10 liters will be thrown on the ground. So if you do that, this is what you find. The pixels, remember, if you split this image, you can cut it in the vertical axis into small pixels and in the horizontal axis, and one small square is 1 pixel. Now look at those points where the bright stars are. Bright stars are releasing more photons towards your telescope. The more photon they release, the pixel exactly pointing to that will receive that photon. But because it's releasing more photon, it will fill up quicker. When it fill up quicker, the remaining photons you throw into it will be spilled over, okay, to adjacent pixels, and they can fill up that line, that column of pixel. And we call that blooming. Okay. Some of you see it, you've taken photos that look like this. You take a shot. If you follow space telescope, like the James Webb telescope, when the first images were made, they had spikes all around it. Those spikes are just as a result of blooming on those pixels. This is what you will see in a dark current. Okay. If you have dark current in these pixels, which means you have electrons not coming from silicon, electrons coming from your device itself, then they fill up this pixel. If you take an image, those pixels will become dark in itself. So if you took image of the dark current and then you take image of your source and it looks like this, you can subtract image of your dark current from this, and then your image will look nice. That's how we correct dark current. Okay, so these are just examples of optical images taking. You see bright columns, and you will see regions where there are hot spots, which could have some element of blooming, and you see things that are from cosmic rays. Cosmic rays you cannot avoid, they are everywhere. They are constantly ionizing electrons. They get into your CCD and they can sometimes produce bright spots, which are not really galaxies, but they are just electrons from cosmic rays, probably sometimes from the Milky Way, sometimes from outside the Milky Way. Okay, so I recommend you look at every astronomical optical image you see these days before proper calibration. Maybe you see the one they have calibrated and corrected for the dark current, the dark columns, hotspot. This is what they typically look like, okay? And when you process the data, you can remove those bad effects. How do you process astronomical image? Well, you need to take at least four shots. One is the raw image of your source. Two is image we call the bias image. Three is a dark field, the one I say you take when your shutter is closed. And there's also what you call the flat field. The flat field is image you take in a uniformly lit field. Call it twilight. I hope you know what twilight is. It's just that time before it gets completely dark. The sun has set, you can't see the sun again, but the rays of the sun still comes out in the horizon. So most of the light there is uniformly distributed. Okay, so you need flat field. When you take that, let me quickly go because I want to go to radio astronomy so I don't use up all the time. So you take a raw image, you take a dark frame, okay? You subtract the dark frame from the raw image, and then you get that image. You subtract the flat field, sorry, the bias from the flat field, you get flat minus bias. And then the way you get your final image is to take the first one and divide it by the second one. And then you get your final output image. So astronomers don't just take pictures. They do certain things that we call calibration. And this is just simple steps. Okay, so after doing that, if you have some extra things that you need to flag, you may identify some pixels that you don't need and remove them if they are completely bad. Optical astronomy does not all take images in all bands at the same time. Remember I said optical light you can spread from red all the way to violet. Okay, so we have different filters. Just like if you don't want UV to get into your eyes, you wear a sunshade and the light you see is now very, very comfortable to look at. The same way we filter out different bands and then we take specific images from specific band, like in the B, there's a U, B, V, I, R, and so on. So those are just filters you put behind to remove some wavelengths and capture specific ones. Okay, that's where I will stop for optical. Are there questions for me?
Yeah, we have 3 questions on chat.
Okay, let me see.
The first one, okay, you can see it from there?
Yes.
Okay, the last 3 questions there.
After counting, where are these photoelectrons disposed? Well, you count, you record the data, you throw away, you drain. Draining is just throwing it away. You're recording the number of photons. Okay. Or do they not have any effects? I don't know what you mean by effects if you're going to just dump them, delete them. How can the photon with energy greater than the energy gap between this affect the counting? I don't completely understand. Jonas, this is from you. Can you explain your question more?
Yeah, as we know that when the electron falling on the plate with the energy equal to the energy gap, it means it will knock out an electron. But what if the falling photon has energy greater than that energy gap?
Yeah, okay. So if it has, remember the band gap is 1.26 electron volts. So if you bring in 2.26 electron volts, the silicon will absorb 1.26, and what is left is 1 electron volt, and that is not sufficient to knock off another electron. So you can only knock off 1 electron. Okay, and the rest of the energy will be transparent. Okay, how are the effect of blooming corrected? To fix blooming, you remember that blooming is caused by this bright patch and let me find something. Where is the blooming image that I had? That one, okay? So in this case, if you want to correct this, remember, if you expose the CCD camera, the pixel longer, then it fills up. So it means you can reduce the exposure time on this, then blooming, then you will not fill up the bucket. Okay. If you put bucket on a tap and turn it on, it takes 1 hour to fill. After 1 hour, everything else is pouring on the ground. So if you want to go fill that bucket in that place, make sure that you put the bucket on the tap for less than 1 hour, and then you're fine. There'll be no pouring of water. Okay. So reducing the exposure time is one way you can remove blooming. What do I mean by pixel? Wait. How are the, okay, answer that. It's used for this kind of editing. The optical astronomers use IRAF. I hate IRAF, so I use Python.
I think there is also a Python version of IRAF, which they call PyRAF. But it's still, anyway, it's still almost the same with.
Yeah, I use purely Python. I don't use PyRAF at all. So
okay.
I use photoutils in Python. But please don't mistake me for an optical astronomer. I don't like staying awake at night. Sorry. Okay, what do you mean by pixel of 2024 in this slide? Well, 2024 simply, let's assume that one axis is 2024, the other axis is also 48. So it's 2048 by 2048 pixels. Okay. Thank you for explaining. Thank you. Okay.
Then we have one raised hand, starting with Inyama, then Aman.
Okay, you guys must remember I still have radio astronomy to teach.
2 raised hands.
Go ahead, no problem.
All right, thank you.
We'll take one question each. Inyama, one question. Aman, one question. Go ahead, very brief. Inyama, go ahead.
Can you try to, wait, before they start, can you try to remove this line? I'm seeing it's irritating me, sorry. But yeah, I don't know.
Also irritating me. I've looked at it. I don't
Okay,
know
go
how
ahead.
to remove it.
Let me stop sharing. Maybe that goes away and I start again. Go ahead.
Okay.
Who?
All right, Prof.
Inyama, go ahead.
Yes, sir. So about the energy that the photon energies that are higher than the band gap. So my knowledge is, hello, can you get me?
Yes.
Go ahead, we can hear you.
Yes. So my knowledge is from solar cell photovoltaics, and what I understand from that is that those energies will cause thermalization, which just means that they'll cause it to heat up. So I was wondering if it's the same solution with the heating up that comes from the electric charge that is supplied to the CCD, or the filter that you mentioned last deals with that. Because in solar cells, what they just is to put a higher one with higher band gap on top of the other one with lower band gap.
Yeah, so if you keep the difference in the energy in the system, then it causes thermalization. But if the remaining energy doesn't stay in the system, then it has no impact, right? Remember, if it's like throwing, what example can I, two cars hitting each other, okay? You carry the kinetic energy from the two vehicles and then you hit. Now, in most cases, you will expect that this will cause only damages. No, the energy conversion from the kinetic energy of the two cars doesn't go all into damaging the vehicles. Some of it are emitted in form of sound. Some will go away in form of heat, okay? Only few is converted to mechanical energy that stays in the system and causes the damage. Now, if you send in a photon that carries more energy than 1.6, the moment the electron acquires 1.26 electron volts, it will jump. If the rest of the energy is not injected in the system, it does not thermalize the electron. If it is, then it does thermalize the electron. That's just giving it additional kinetic energy. So it moves faster in the conduction band if the energy, the balance of the energy stays in the system. Is that?
Thank you. Thank you very much.
Okay.
Aman, very brief question, just very brief so that we can move on with radio astronomy.
Okay, my brief question is, how would the robots or machines count the electrons?
How would they
Yeah.
count it?
Yes.
Oh, just the same way you count numbers.
Oh, so
Yeah.
the robots would count in the way of the conveyor belt with the water bucket system. That's how they would count.
Yes. The
Oh.
conveyor belt is just an illustration to show you this is counted sequentially, okay? You don't just pick a bucket anywhere inside the array of 1,000 by 1,000. You make sure it's done sequentially, so when you count, you exactly can tell where the number of photons you've counted came from.
So this is mostly done by machines, right? Not humans.
Of course, this is an electronic system, yes.
Thank you, Professor.
All right, thanks. Okay, I guess I can go to my next lecture. I hope I can be shorter than this. Let's see.
Sure.
Just one moment. Oops, techniques. That one. Okay, so in this part of the lecture, I'll be super quick so that Dr. Shuge can take you through spectroscopy. I'll introduce you to my favorite thing, which is radio astronomy. Again, as I said, I hate staying awake at night, so I don't venture, well, I do sometimes, but I don't like optical astronomy. Okay, this is one of the reasons you should care about radio astronomy, because Africa will be hosting the largest radio astronomy project, which is called the Square Kilometer Array. And the meerkats, which you're seeing here, which is 64 dishes, each one of them 13.5 in diameter, 13.5 meters in diameter, is already fully operational and chunking out huge amount of spectacular science. But because it's a short program, I'll take you through a bit of a history of radio astronomy, and then I'll show you what radio astronomy is all about and why we don't do photon counting in radio astronomy. First, in 1932, Karl Jansky, who is not a radio astronomer himself, he's a telecom engineer. He worked for Bell Laboratory. That's the picture on the bottom right corner. Built that antenna. This was, if you remember, this was still during the World War period. So people were using antennas to spy on each other to pick up their radio waves or to eavesdrop on the communications. But he kept seeing this emission that keeps reoccurring every 24 hours on his antenna. And it turns out that the emission he was detecting at 20 megahertz was actually coming from our galaxy. In fact, later on, we found out that he was detecting emission from the center of our galaxy, which contains a black hole. 6 years later, Groth Reber built, he's actually the first proper radio astronomer, built a 10-meter parabolic dish. Of course, by this time, they already learned from the optical astronomers that you shouldn't build a spherical dishes of spherical mirrors. So They moved from spherical to parabolic dishes, and he was able to make the first map of the Milky Way at 160 megahertz. By the 1950s, we were already detecting discrete sources. Remember, with a 10-meter telescope, everything you see will be elongated, right? The resolution is not there. Resolution is lambda over d, so you don't have sufficient resolution. So by the 1950s, we were improving building larger dishes and beginning to see discrete sources. By the 60s, we know what radio interferometry is. By the 70s and 80s, we are doing imaging. In fact, the VLA was built in the 70s. VLA is Very Large Array, which is in Socorro in New Mexico State in the United States. By early 2000s, we're developing software receivers, software-based receivers. And in 1991, just before early 2000s, the idea of SKA was conceived. Can imagine how many of you who were born before 1991, but the construction of this telescope just started 2 years ago and should be ready for use by 2028 or maybe 2030. So that's a bit of the history. The first 10-meter parabolic dish is the one you see on the top right corner there. So here is the EM spectrum. Everything I told you in the beginning part is just within that small white patch that you spread from red to violet, right? That's your light. That's very boring. Look at the radio band. The radio band is spectacularly spread, actually covers almost the region covered by infrared, optical, UV, and X-ray combined. So you have a wide range of frequency from which you can observe. Of course, I'll tell you the disadvantage later on. We do not use all of it. We use the microwave, which is from 1 centimeter in wavelength. You see wavelength and frequency written. You can use that, or astronomers use that interchangeably, because if you just use speed of light, you can convert one to the other. Okay? Millimeter, that is one very close to infrared, right? Good. So if you go to the far infrared, the millimeter band is just there, around 1 millimeter. So if you get to 1 micrometer, which is sub-millimeter, you're almost in the infrared regime. Sub-millimeter, I just mentioned that, anything below 1 millimeter up to 0.4 millimeters. Okay, so that's the frequency band that I refer to. If I say radio, I'm referring to that. The question will be, why don't we use wavelengths longer than 30 meters? Well, this will answer that question. This is what we call the atmospheric window, or transparency of the atmosphere. We never build gamma ray telescopes on the ground. Gamma rays are very high frequency, extremely short wavelength, 10 to the power minus 14 meters. Those, we don't pray that they come through the atmosphere and get to us. That would damage the cells of your body. Okay, that will kill off humans. X-rays, same. I mean, those are very dangerous to your skin, to your organs and everything. But we can see that the white line pattern just shows that our atmosphere is not transparent, it's opaque, or doesn't let it penetrate and get to us. So you need to build telescopes that detect photons in that wavelengths and put them in space above our atmosphere. In UV, some part of UV, well, most part of UV is all of them. It's not detectable from the ground. UV sometimes penetrates, especially the ones that affect your eyes in the sun. But those are just extremely too faint. Well, probably can be detected with some form of optical. But all UV instruments are in space. Optical, yes, you can do from the ground. Bearing in mind that changing weather condition could actually make you waste your night in the observatory and not be able to do any observations. If you come down to infrared, a large part of infrared, a small fraction of infrared can be observed from the ground. Most part of it, including the one you do with the James Webb telescope, need you to go to space. You can see that up to 4,040 kilometers above the ground, there is a block of white patch, okay? That means you can't observe. Millimeter ALMA can be done on the ground. There are some specific areas where you have water molecule emission, which can obstruct things, but otherwise everything can be done on the ground if you have dry conditions. The rest of the long radio waves is clean. You can do everything from the ground, no obstruction, except where you have a white line to the left that corresponds to wavelength of 30 meters. And you can see everything is cut out, okay? You will need to cross the layer of our ionosphere to be able to observe at any wavelength longer than 30 meters. To be honest, I always tell my students, if you really want to dream big and win spectacular prizes, try to explore the physics behind emissions at 30 meters and above, which we do not know and have never observed. So that means you need to fight for funding, find a lot of money, build a telescope, a space telescope that can stay at high altitudes and put them above our ionosphere and observe radio waves at above 30 meters. That already could win you a Nobel Prize. And who knows, you might discover a physics that we don't know already. But there is no astronomy we've done in radio band that is at wavelength that is longer than 30 meters, because we've been observing from the ground, and wavelength above 30 meters cannot get to us on the ground. Well, we brag a lot in radio that our band is clean. Yes, it is, but we have interference from lots of things. We don't like water. That's our worst enemy. The plot you see here is real data taken from the Green Bank telescope in West Virginia in the United States. It's a 100-meter telescope. And the vertical axis just shows you the zenith opacity. Zenith is just if you point vertically upwards, okay? Opacity is how opaque the environment. If it's very opaque, it's 1. If it's less opaque, it's less than 1. Good. So if you look at all the solid line is a total, a combination of all the other lines, but the dashed line, dash and dot, dotted lines, and the other line. So these things contribute different levels of obstruction to radio waves. They do not completely exterminate the radio waves, but they absorb and scatter some of it, okay? So what you get after interaction of radio waves with water molecule is not what is emitted, okay? It's weaker than what is emitted because some of it has been scattered off. Okay, cool. So while you keep in mind that we can observe both day and night, because we don't care about the sun shining or being dark. In fact, if it's dark, it's better because it's cooler, your receiver is performing better. But we have these oxygen, hydrosols, dry air, water vapor, all affecting our radio waves, but they don't stop us. These are the bands I've mentioned earlier. Sorry, I have to run really quickly because I see I've almost taken 2 hours. And I don't want to be selfish. Okay, so we do astronomy at low frequency. We do a fairly high frequency. We use terminologies like bands to describe different frequencies we observe at, like the L to Q band. In the case of ALMA telescope, the one you see on the top left, that is very high frequencies. We use band 1 to band 10 to describe them, but where band 10 is very high frequencies going to nearly 1 terahertz. 1 terahertz is 1,000 gigahertz. Okay, how much energy? We've talked about optical photon. Now, in the case of radio photon, how much energy do they carry? Well, you can do the maths, right? We've done the earlier maths and said, well, if you have lambda at 600 nanometers, or you can use 900 nanometers, you can use Planck's constant, okay? Convert wavelength to frequency and multiply it out. And then you have the energy, and then you can convert that to electron volts. So typically, optical photon at 600 nanometers will have 2 electron volts. If you use KT is also thermal energy, right? If you assume that the quantum, the h nu energy is equal to KT, then K is your Boltzmann's constant, right? Then you can derive the temperature. So the typical brightness temperature, this is not the thermometer, the heat temperature, this is the brightness temperature, okay? Not really brightness, it's actually temperature. Is 20,000 Kelvin. Okay. Now, if you do the same for radio waves at wavelength of 1 meter, you have 10 to the power minus 6 electron volts, and that's equivalent to 0.012 Kelvin. 10 to the power minus 6 electron volts is not capable of knocking off an electron from silicon to make it jump to conduction band. So if you incident that on silicon, it will just be transparent. The radio wave will pass through like it never existed. Therefore, in astronomy, we don't have the option of doing photon counting. Well, as somebody mentioned, maybe I know what technology is today. I know what it will likely be in 50 years. Maybe in 100 years, somebody might develop a material that this tiny energy can knock off electron in that material. And maybe we can start taking snapshots in radio waves. Then it means if you make a phone call, I can intercept the phone call and image the radio waves your phone is emitting, which will be cool. This is all I have explained now, okay? For CCD, yes, direct imaging, 1.26 electron volts, that's fine. 10 to the power minus 6 electron volts, not relevant in any way to silicon, doesn't care. So since we cannot directly count the photons knocked out of an atom by radio photons, or the electrons knocked out of an atom, I don't care if it's silicon or any other atom, how then do we measure radio waves or radio observations? Well, we don't do photon counting, okay? What we simply do is to measure the voltage oscillation that is induced in a conductor by an incoming radio electromagnetic wave. Okay, that may sound so strange. Yes, I understand. Think about your radio set. The antenna in your radio set, okay, is a conductor. When the radio waves transmitted from a radio station, maybe a radio tower, is incident on that, then it generates small millivolts, okay? Millivolts of electric charges. And because the radio waves sent by the station is modulated, then it means this voltage will be oscillating in different ways depending on the modulation. Now, astronomical objects also emit radio waves that oscillate, of course, not modulated like that of humans. So when we observe with radio telescopes, we are not counting photons. We are simply tracking and measuring the voltage oscillations that is induced in the antennas we use. Radio telescopes are just mere antennas. They have huge reflectors because you want to collect more of the radio waves and incident it on the antenna, which is usually in a system, a component we call the feed horn. Why is radio interesting? Well, if you think about our galaxy, the picture on the top right is optical image of our galaxy. You would see dark patches everywhere, but the one below is radio. Radio waves don't have any color, so don't ask me why is it in blue, red, and yellow, and white. Those are just what we call pseudo colors, okay? Regions with high radio emission intensities are represented as white. Lower ones is orange, much lower one is yellow, much lower one is red, much lower one is blue. So Wherever you see any color on the bottom right image is radio emission, just the intensity is represented by colors. And the other question I have received before is, why is the image of our galaxy just like a straight line in the optical? Well, that's because we live in that galaxy, okay? You're looking at the galaxy from where we live, therefore you see just a line of the thick disk of the Milky Way. But the Milky Way we know is a spiral galaxy. I'm very sure of that. But anywhere you see a picture of the Milky Way, tell them it's a lie, because we live inside the Milky Way. We don't truly know what it looks like. However, we're measuring distances to different stars within the Milky Way and reconstructing the 3D shape. And we know the Milky Way has spiral arms, but we don't know how many arms and what shape they are. We have no idea. So everything you see when you Google Milky Way is artistic impression, okay? It's not a real picture, including this one I have used here. The one below is real, it's an Andromeda, but the one on top is fake. It's artistic impression, not fake. Okay, here is where you should care about radio. If we never had radio astronomy and you observe this galaxy, it's called Centaurus A, you probably know about it, okay? This is what you will see. And if there was no radio, this is all you will know about this galaxy. You will know that there is a very bright spot around the center. That's where the supermassive black hole in this galaxy belong. And there is some patches of black things. Those black things are just dust. The dust is obscuring the light from the background, okay? So I always use this illustration and I keep using it. If you drive your fancy car behind a truck carrying a tipper load of sand, and it's a rickety truck and it's chunking out black smoke, everything ahead of you will not be seen. Not because they are not reflecting light or there is no light bulb on the other end, but because all the lights are being absorbed by the black smoke. So that's what's happening here. In this case, it's not smoke, it's actually dust particles. They are made up of silicate and carbonate materials. Again, you will know that this galaxy has a disk, as you see in the dark patch, and has a black hole that is, driving lots of light emission, lots of activities around the center, and that's all you will know, okay? But if you observe this same object with radio, you will not see the things that you see in optical. You will see what I have just shown now. You see what looks like a jet, what we call synchrotron emission. That's strange. The strange thing is, it's not the disk, okay? It's rather perpendicular to the disk, so it's something else. Therefore, if you combine the two images, you'll understand that the optical gives you information about the disk, the dusty disk where a lot of stars are forming within the galaxy, but the radio gives you information about the synchrotron emission coming from the black hole, which we call jet, and that jet in most cases are a couple of tens of times larger in size than the galaxy itself. So if we remove radio astronomy from the picture, remember radio astronomy is less than 100 years old, which is surprising. I mean, it has achieved a lot, but it's just less than 100 years. It needs another roughly 10 years, 8 years to turn 100. And I hope people will celebrate that a lot. That's not all. I want to ask a question here. This is an optical image, okay? Can anyone unmute and tell me what they see? If you're doing your research and you observe this region of the sky and you find this, what would you think? What would be your interpretation? I need at least 2 comments, then I can move on.
Julius, go ahead.
So I think it can either be a spiral galaxy or a nebula. I don't know. It looks so sharp.
Oh, the central one is a spiral galaxy, has an arm. There are other objects, some of them very far away, some of them nearby. At least 2 other bright satellites, maybe galaxies, and so on. Okay. That's the much you can say from optical image on this, right? There are galaxies. And then what? We have trillions of them. So it's not that interesting. But if you observe this region at radio frequency of 21 centimeters and detect neutral hydrogen, this is what you see. So this is drawn to scale. You clearly see that there is hydrogen gas in the spiral galaxy, because tracing the spiral arm. But what is interesting is that you see this nice blue trail of hydrogen gas connecting the central galaxy that has spiral in the optical to the small one that is on the bottom left and to the top one that is on the just at the top of the central object. So we call this tidal interaction. These galaxies separated by huge distances are interacting with each other. And there is no way we would have known that from optical observation. Only radio can show you that. Okay? Do you see that? I hope yes. I can't see or hear anybody. Okay. Cool. So the next thing I'll do is to explain how radio waves are emitted. I'll tell you a bit about telescopes and then I'll stop. Okay. Sorry for keeping you long. I typically don't give long lectures. Okay. So radio waves are of two kinds. You have the continuous emission, which is usually broadband and cover a wide range of frequencies. I've used the optical counterpart to show you it covers red to violet. Okay, let's continue. Broadband typically occur as a result of acceleration of a charged particle that is moving in a wide range of energies. The wide range of energies means you have a wide range of frequencies, right? Because energy is h nu. Good. So if you have energy 1, 2, 3, 4, 5, 6 to a million, then it means there'll be new 1 to a million, and that's broadband. Okay, the spectral line is usually narrow band, and it happens. Yes. Is there a question?
Is raising hand. I think maybe the person had. Go ahead.
Okay.
No raised hand. Go ahead with your lectures. There's no.
Okay, good. So spectral line is typically narrow band, and it occurs as a result of quantum mechanical principle. If you've done quantum mechanics, okay, let me state again, you cannot do astronomy without quantum mechanics. So we know that the energy levels that a particle in an atom or a molecule can take is quantized. It means they are discrete, okay? It's not continuous. Can have energy level 0, 1, 2, 3. It's not a smooth rise energy, okay? So it's discrete. Now, these transitions, if you have atoms or particles in an atom jump between one transition and another, they can emit radio waves corresponding to the energy they release or absorb in jumping up or coming down. So going back to continuum, continuum emission can be again of two types. There is the thermal emission and there is non-thermal emission. For the thermal emission, you always hear about black body radiation. I know students usually have blockages when they hear black body radiation, but this is very simple. If you take the Planck's distribution function, which I've written on the bottom left, okay, the B lambda into lambda plus T, because this thermal emission is as a result of the temperature of the body. So it must be related to wavelength or frequency. Remember, it's broadband, okay? And then the body must have a temperature. So it means that if you can take a range of wavelengths of frequencies and you take a temperature of a body, then you can compute brightness of the body. So the higher the temperature, as you would see, the more the peak in the plots you see on the right-hand side, the more the peak shifts to higher frequencies. The lowest temperature emission that we know is a cosmic microwave background, and it's 2.7 Kelvin. Okay, so we approximate it to 3 Kelvin, and if you plug 3 Kelvin into the equation and determine the brightness for a wide range of frequencies, then you find a red curve. Your body is 36.7 or 36.8, approximately 37 degrees Celsius, which is 310 Kelvin. So your body gives out emission with a black body spectrum in orange. The sun does the yellow one, and a massive star with a surface temperature of 100 Kelvin will produce the blue one. You probably do know that we have what we call the Rayleigh-Jean approximation. Well, Rayleigh-Jean approximation simply says if the energy h nu is much, much less than kT energy, then this whole equation, okay, becomes equivalent to this. Remember, I can rewrite this in form of nu frequency or in form of wavelength. Okay. No problem, I guess. Cool. So this is one kind of way you emit radio waves. And the bodies that emit this way are typically dust within the galaxy. They are heated up by the photon, and then they re-emit at longer wavelengths. And most of that is thermal blackbody. Well, blackbody is a perfect system that absorbs everything and emits everything. So most of the real blackbody emissions are not perfect black bodies. They typically classified as gray bodies, and there are equations to justify that. The second type of thermal emission is called Bremsstrahlung. Bremsstrahlung is a German word that stands for free. If you take hydrogen atom, which is made up of proton that is heavier, and then an electron, and you heat it up, you break the bond, okay? You knock off the electron. So this positively charged particle is considered heavier and doesn't move or move slower than the electron. The electron is lighter and moves faster. If electron in a cloud of positively charged particle and of course other negatively charged particle approaches a positively charged, the red one, and is attracted and trapped, then this becomes hydrogen again. But that's not the scenario we're describing here. When it's trapped, it emits H alpha, which is spectral line. But when it's not trapped, it's pulled towards it, but not trapped, but deflected. So this has an energy 1 going this way, but by the time it's deflected, it goes that way, okay? So there's energy 1 and energy 2 for this electron. The difference in the energy is this emission that goes off. Because there's a difference in energy. Energy is h nu. So if you divide the energy by nu, you find the frequency of this radio emission. And that is called free. Free because it's free proton, free electron interaction, not trapping. Okay.
Okay, Prof, on that graph, somebody asked what is the meaning of DSTV?
Okay. The DSTV is the DSTV, you know. I just put the line here of the frequency at which your DSTV operates.
Okay, and if possible, maybe we need to wrap up radio astronomy around 1 p.m., I guess.
In 6 minutes, right?
Yeah, 6-7
Okay.
minutes. Yeah.
Wait. In 6 minutes from now, right?
Yes.
Okay. Yeah, so I'm definitely aiming for that. Okay, so I'll be quicker. This is all I have described. Energy 1, energy 2 gives you the free. The third one is synchrotron emission. I will just ask you to look up this by yourself, but this has nothing to do with heating. It's as a result of relativistic electron getting coupled in the magnetic field. And each time it does a spin around the magnetic field, it gets a kick, which is just some kind of acceleration. Okay, acceleration is changing energy or changing velocity, which corresponds to changing energy, and there is emission that goes off. Spectral line is the most famous one is hydrogen. It happens as a result of changing spin direction of electron and proton within hydrogen atom. The molecular lines are due to rotational or vibrational states of a molecule, and masers. It would take me a long time to explain that, but it's just microwave. It's equivalent of laser, but replace light in laser with microwave, and it occurs as a result of population inversion. When we talk about vibrational states, it can be different kinds of vibration, but again, I've got just 5 minutes. I wouldn't focus on that, but this radio astronomy is my specialty. Ask me any question at any time. So when you observe at these different wavelengths, what are the sort of things you look at? Spectral line, you might be looking at molecular cloud, maybe dense molecular clouds where massive stars form. For synchrotron, you're looking at jets, supernova shocks, things that are tracing magnetic field in the cosmic space are things you trace. How do we know which continuum is coming from? If you observe a galaxy, how would you know which continuum is coming from free, from thermal process or dust, and which one is coming from synchrotron? We use what we call spectral index. It's simply how your flux or flux densities is changing with time. Okay. So this is M82. It's a famous starburst galaxy. It means that this galaxy is forming a lot of stars. If you observe it at different frequencies, you see it drops, okay, and then rises. So I'll describe that's the overall spectrum. The blue one has spectral index of minus 0.8, and you can see it's negative slope. Anything negative slope like that with minus 0.8 up to minus 2 usually come from synchrotron emission. So it could be from the jet, from exploded supernova shocks that emit this kind of emission within the galaxy. This has a positive spectral index, B plus beta. Positive, of course, the slope is positive. And this typically is from black body radiation, and it's dust that has been emission from dust that has been heated up by UV photons from massive stars. That has minus 0.1. It's almost flat. This typically come from thermal free emission. Okay. They have low negative or very low positive values, and it's caused by hydrogen that are ionized by UV photons from very massive stars. Okay, I'll leave you to have a look at textbooks on radiative transfer, but keep in mind that radio waves you pick up from Earth, and even if it's from the sun, remember, if you observe anything, the light you see from the sun now has been traveling for about 8 minutes, okay? So it has interacted with a lot of things, and we use these typical radiative transfer equations to describe what has happened between the source and what we detect. And that is just described by what we call emission coefficients and absorption coefficients. Okay, if you combine those two, you generate radiative transfer equation. This is more complex than this. You will need to bring in what we call Einstein's coefficients in deriving some of these equations. Telescopes. This is just a schematic. We use parabolic dishes, and the aim is to focus everything in the sub-reflector, and the sub-reflector focus everything in the feed horn. It is within the feed horn that you have the antenna. The main reflector, the primary parabola, is more just to collect as much radio waves as you can. Remember, radio waves are extremely faint. We amplify the signal, we mix it down convert, change from analog to digital, then record the data and process it with computer to make images. Okay, so I won't go into these a lot. I've described Nesmith. This is just illustration of prime focus, and the things I talked about in optical, they are same for radio, except that we do different parts of this for different reasons. I won't talk about surface efficiency. Sorry, I was too slow in the optical part. I'll leave you with this last equation and say when you pick up an emission from a telescope, we usually measure what we call system noise temperature and antenna temperatures. Antennas don't generate temperature, they're not thermometers. So we use noise diodes to convert counts per hertz. We use counts per megahertz, okay? It's just an arbitrary value. It's not that we're counting the photons, okay? But you take a noise diode with no noise temperature, you inject the signal into your system and you use it to scale the power densities you measure to Kelvin, okay? So that's how we get this. But of course, any measurement you take is a combination of what is coming from the cosmic microwave background, which you cannot exclude. It must come into your beam. What comes from the receiver, what comes from the atmosphere, what comes from your target, what comes from your spillover, and so on. So the system noise temperature is all these things combined, okay? And you need to slowly sort each one of them out and extract what is from your source before you calibrate. It's exactly my time. I'm sorry I have to stop, but please, I'll write my email address.
Okay, thank you, Professor James, for the talk. We have a Slack workspace, and I would encourage participants to send remaining questions to the Slack workspace. Maybe at his convenience, he may be able to attend to them.
Yes,
Then,
please.
before you leave the meeting, James, I would want you to just talk briefly on something as an experienced observer. What advice would you give participants on how to prepare a successful proposal? Actually, I am aware that is something that can take even hours to discuss, but maybe just your advice, because some of these telescopes need observation proposal that go through some evaluation and selection. So what are
Okay, yeah. Yes, I'm happy you agree that this is something that we can talk for 1 year and never finish. But the first recommendation is don't submit a proposal until you've read papers related to what you want to do. Because the same way you sit down and want to do something is the way there are, I think, over 20 or 30,000 astronomers globally. Somebody might already in the past have thought about it or done it, or maybe didn't complete it. So don't say, oh, I think this idea is brilliant, and you suddenly think you're the only one who have ever thought about it. Of course, there are those ideas that you're the only one who have thought about it, but it's always good to read the papers. So you don't submit proposal, the referee will say, but we have this result before. That's one. Two, understand the system you want to submit proposals to. I have received proposals that I rejected for telescopes in Europe, and the person wants to observe a source that the declination is -70. Those kind of sources, you know, the Earth's equator is here. You can only observe with telescopes below the Earth's equator in the southern hemisphere. So you must know the instrument, what are the capabilities. If I have a 20 gigahertz receiver in my telescope and you apply to use the telescope and you are asking me to observe at 40 gigahertz, I'll throw the proposal in trash because you definitely did not read about my telescope before applying. So understand, those are the basic things first. Well, the second thing is to present clarity. A lot of people submit proposals that are good. The science they want to do is good, but they want the reviewers to complete their sentences or to beef up the proposal for them. No, don't assume we know anything about what you want to do. Describe all of it in details. The third one is show that you have the capacity to complete the science if you're given the time. It's not enough to write a proposal that will produce scientific result that will win you a Nobel Prize, but not show that when we give you the telescope time that you can analyze the data. So if you have in the past published a result with similar proposal, mention it. Well, please be careful. That statement may be wrong. If they say they are doing double-blind system, double-blind means your name, the names of you and your co-investigators will be removed from the proposal because they do not want the reviewers to know who is submitting the proposal. So you don't want sentences like, in the work we did in 2022, we found this. If you use we, then you are slowly identifying who you are and what you do. So people can already tell, okay, which group this is. So, but otherwise, use a descriptive manner that doesn't reveal your identity in the case of double-blind proposal to show that your team, you and those who are proposing the work, are capable of producing results. Remember, we have petabytes. Oh man, sorry. I have another meeting. Just one moment. This, I'm very sorry. Okay, so be sure that you can prove that you can do the science. And if there are models you need to use, explain them properly. If you're going to use that model to explain the data when you receive it. I think those are the basic ones. Have clarity in what you're writing. Don't assume that the reviewers are professionals, they should understand. Yes, we understand what you want to do, but if you don't write that you're going to do it, we assume you don't know you need to do it. Okay, don't know if I answered.
Thank you very much. I think participants, if you are interested in knowing more about even proposals and you have questions there, you can still send it on Slack. I think most of these things will be attended to at their convenience. Then thank you very much for your lectures. And maybe you can, yeah.
Yes, Dr. Shoge.
So I think we'll be giving 20 minutes break. Yeah, 20 minutes break. You come back here at 1:37. Oh, hold on, 1:27, please. 1:27 p.m. So in 20-minute time, Dr. Shoge will be starting spectroscopy.
Okay, Dr.
Hope you can hear me, right?
Oh, yes, I can hear.
Oh, cool.
Okay, so you'll be starting at 1:27.
Okay.
Dr. Shoge, yeah, it would be nice to, it's nice meeting you electronically. Sorry that Mama is Julius. I know plenty of people here.
There are a lot of activities that will require the attention of people like you. And yeah, just be ready to answer our call anytime we call on you again. Thank you so much.
Okay, thank you. And be patient with me with all the irregularities of my schedule, but yeah, I'm always happy to oblige any request.
Good. Thank you so much.
Thank you.
All right. Okay. On that note, bye everyone. And I've dropped my email and I'll also look at the Slack and respond to questions. Okay. Bye everyone.
Yeah.
Thank you so
Bye.
much.
Thank you.
Bye-bye.
Hi, everyone. Can you hear me?
Yes.
We
Okay.
can.
You are welcome back from the break. We're continuing with our second lecture of the day, and it's going to be delivered by Dr. Mansurat Shoge. Dr. Shoge is a lecturer at the Department of Chemistry at FAST Institute and Technology. FAST Institute of Technology, Kaduna, in Nigeria. Incidentally, she's the current head of department of chemistry, and she specializes in, among other things, astrochemistry. So, Dr. Shoge, over to you.
Good morning, everyone. Oh, sorry. Good afternoon, everyone.
Good afternoon. I think
I'm
depending
trying
on
to
time zone,
share
there could
my
still be some people in. So you can share your
exactly.
slide.
Okay.
We are yet to see the slide. If you've done that, if you've shared it already.
I'm checking. Okay.
If there is any challenge, you may let us know. If it entails sharing from
Can
here,
I send it to you?
I have it already. I can share it while you present, and
No, I have the updated one.
okay, go ahead.
Okay. Thank you.
Hello, Christian.
Yes.
Sorry, I think you can share the slide, the one you have there.
I have sent it to you.
Okay.
While she continues with the presentation, probably after the lecture, she can send to us the updated slide so that it can be uploaded.
Okay.
I think that will save us time and whatever.
I have sent you the updated one. Just wait. Sorry, it's uploading.
Well, sorry for the technical glitches. Just a minute. Let's sort out this.
Can I start?
Yeah. Hello, Christian.
Go
Hello.
ahead. Go ahead.
Okay. Good morning, everyone. Sorry for the little delay. My name is Dr. Shoga Mansurat from Air Force Institute of Technology. I will be lecturing you on stellar spectroscopy. Stellar spectroscopy is a branch of observational spectroscopy. Sorry. Okay. Stellar spectroscopy is a branch of observational spectroscopy. So before we go into stellar spectroscopy, let's take a look at observational spectroscopy. Astronomy. Observational astronomy is the practice of studying celestial objects, usually stars, planets, galaxies, and cosmic phenomena by collecting and analyzing electromagnetic radiation, which include light. Electromagnetic radiation is a form of energy that travels through space as waves. It consists of electric and magnetic fields that oscillate perpendicular to each other and to the direction of the wave travel. Examples include visible light, radio waves, X-rays, and microwaves. The key concept here in observational astronomy is light as a messenger. Light travels across vast cosmic distances, bringing information about the source. We have electromagnetic spectrum, which is observational astronomy, which uses various aspects such as the radio wave, such as the radio wave, the infrared, visible, ultraviolet, X-rays, and gamma rays to study different aspects of celestial objects. Then types of observatories here can be ground-based, such as the radio telescope, or the space-based, such as the Hubble Space Telescope, depending on the type of radiation being studied. Branches of observational astronomy are the optical astronomy, which focuses on visible light to observe stars, planets, and galaxies. Visible light is a type of electromagnetic radiation that can be seen by the human eye. It falls within a specific range of wavelengths, approximately 400 to 700 nanometer. This range includes all colors of the rainbow, such as the red, orange, green, blue, indigo, and the violet. So let's go into the next, which is the stellar spectroscopy. Stellar spectroscopy is the study of the light emitted by stars. So by analyzing this light, scientists can learn about the star's composition, the temperature, motion, and other properties. When light from a star is passed through a prism or spectrometer, it is splitted into a spectrum of colors. This spectrum often contains dark lines, which are called the absorption lines. These lines reveal what elements are present in the star because each element absorbs light at specific wavelength. For example, we have hydrogen, which produces certain dark lines at specific points in the spectrum. The brightness and color of the spectrum can indicate the star's temperature. By studying the spectrum, astronomers can also determine the age of the stars and also how fast it is moving towards or away from Earth using the Doppler effect. They can also determine the chemical composition of the star. This method has been a key to understanding the stars and the universe. So mostly stellar spectroscopy is a technique that studies the light, just as I have mentioned. So what is the importance of stellar spectroscopy? It allows us to determine what stars are made of, how hot they are, how they move, and even their age without needing to physically visit them. Spectroscopy also provides insight into distant stars and galaxies, and that they are otherwise. Spectroscopy provide insights into distant stars and galaxies that are otherwise inaccessible. So from the study of this stellar spectroscopy, we can extract the knowledge of or the information about their physical and chemical properties. The physical properties of stars include the size of the stars, the mass of the star, the temperature of the stars, the brightness or the luminosity, and also the colors and the density of the star. The chemical properties include the composition, which is 70% hydrogen and 28% helium, with some amount of heavier elements like carbon, oxygen, and iron. Another chemical properties of these stars are the spectral lines. Each element in a star produces unique absorption lines in the spectrum. We also have the metallicity. This refers to the abundance of elements which are heavier than helium in the star. Stars with high metallicity are usually younger, while older stars have low metallicity. So stars evolve over time, and their physical and chemical properties change depending on their stage in the stellar life cycle. So there are different types of spectra. We have the continuous spectra, just as Prof. James mentioned in his lecture. We have the emission spectrum and also the absorption spectrum. The continuous spectrum are produced by hot, dense objects, e.g. a star's core. It appears as a smooth gradient of colors without interruptions. Emission spectrum are created when atoms or molecules emit light at specific wavelengths, seen as bright light on a dark background. Examples include neon light or glowing gases We have the absorption spectrum. Absorption spectrum are produced when cooler gas absorbs specific wavelengths of light passing through it. It appears as dark lines on a continuous spectrum. Examples are spectra from stars, where outer layers absorb certain wavelengths. So the physics of starlight, sorry, I'm trying to, okay, the physics of starlight, light as a messenger. Light acts as a wave and a particle, carrying energy and information. The key properties here are the wavelength and the frequency. To determine the type of radiation, wavelengths are used to determine the type of radiation, e.g. for visible and ultraviolet light, and also the photons, which are packets of light energy that interact with matter. Another physics of starlight is the black body radiation. Stars emit light as black body radiators. According to the Wien's law and also the Stefan Boltzmann's law, the Wien's law describes the relationship between a star's temperature and the peak wavelength of emitted light. Hotter stars peak at shorter wavelengths, while cooler stars peak at a redder wavelength. According to the Stefan Boltzmann's law, which is E equal to the Stefan Boltzmann's constant times T raised to power 4, where the Stefan Boltzmann constant is a relationship between the temperature to the energy radiated, which states that the total energy radiated by a star is proportional to the fourth power of its temperature. Spectral lines. Unique patterns of light in a star spectrum result from electron transition in atoms. So, sorry, okay. The spectral lines is also one of the physics of starlight. And from these lines, we can see the unique patterns of light in the star spectrum. Let me just present. I'm coming. Okay. Tools for stellar spectroscopy. Okay. The tools for stellar spectroscopy are the telescopes, the spectrometers, and also the detectors. The telescopes collect light from stars, and the types include the optical telescopes, such as the ground-based telescopes and the space telescopes, e.g. James Webb Space Telescope for infrared. Spectrometers. Spectrometers are instruments that spread light into its spectral components using diffraction gratings or prism. They provide detailed spectra for analysis. We also have some detectors, devices like the CCDs, which was mentioned by Prof. James in his lecture, which are the charge-coupled devices, which capture light and convert it into data for computers to analyze. The observations made from these key instruments, these are the ground-based telescope. We face challenges using the ground-based telescope, like the atmospheric turbulence, which affects the images while using a ground-based telescope. For the space telescopes, they usually avoid these issues and can observe wavelengths blocked by the Earth's atmosphere. So applications of stellar spectroscopy. How can we apply this spectroscopy? Spectral classification. Stars are classified into spectral types. We have the O, B, A, F, G, K, and the M, based on their temperature and spectral lines. The O types are usually the hottest type. They are blue stars with few absorption light, while the M types are usually the coolest red stars with many absorption lines. Another technique in stellar spectroscopy is the Doppler effect. The Doppler this Doppler effect is the change in the frequency or wavelength, such as the sound or light observed when the source of the wave moves relative to the observer. So the motion of the stars relative to Earth causes shifts in their spectral lines. We have two types of shifts which can be caused by the Doppler effect. These are the red shifts, where the wavelength stretch when a star moves away, and the blue shift, where the wavelength compress when a star moves towards us. So they are all used to study stellar motion and detect exoplanets. Then chemical abundance analysis. Spectral lines reveal the presence of elements such as hydrogen, helium, and ions. They also help to understand the star formation and evolution. Stellar rotation and magnetic field is another technique in stellar spectroscopy. Okay. Sorry, stellar rotation and magnetic field. Rotation causes line broadening, such as the spread out of lines. Magnetic fields can split spectral lines in a process called the Zeeman's effect. The Zeeman's effect is caused by the interaction of the magnetic field with magnetic moment of electrons in atoms or molecules. Then the next is the applications of stellar spectroscopy. Okay. Stellar spectroscopy is used to determine the composition, temperature, velocity, and magnetic fields of stars by analyzing their light spectra, providing insight into their physical and chemical property. It also helps identify star motion via the Doppler shifts, classify stars, and study stellar evolution, contributing to our understanding of the cosmos. So in summary, applications of this stellar spectroscopy is the first is to understand the stars, the exoplanet detection, galactic studies, and also in cosmology, which measures the redshift. Cosmology measures the redshift to study the expansion of the universe. It also contributes to understanding the dark energy and dark matter. Then challenges in stellar spectroscopy. What are, okay, before the challenges, let's talk about the case study. Case studies in stellar spectroscopy. That's examples of where this spectroscopy has been actively applied. For example, the sun's composition. Helium was first detected in the sun's spectrum in 1868. Providing that spectroscopy could identify elements in stars. Exoplanet discovery. The first exoplanet around the sun-like star was discovered using radial velocity measurements. And also another case study is in the mapping cosmic expansion. According to Edwin Hubble in 1920, he used redshift data to show that galaxies are moving away, leading to the discovery of the expanding universe. So these are the case studies in stellar spectroscopy. So let's move to the challenges in stellar spectroscopy. These challenges include atmospheric distortion. Atmospheric distortion is one of the major challenges in stellar spectroscopy. Difficulty of obtaining high-resolution data due to the vast distances to stars, interference from Earth's atmosphere, complexity of spectral lines in the presence of multiple elements, and physical conditions in a star's atmosphere, the need for precise calibration and potential for contamination by cosmic dust or other celestial bodies can complicate analysis of stellar spectroscopy. Therefore, these are from the atmospheric distortion. The challenges faced are the turbulence in the Earth's atmosphere, light pollution, instrument sensitivity, and data interpretation. So future directions, how can we cope these challenges? To cope these challenges, we can use technological advances such as extreme large telescopes. Large mirrors can provide better resolution and light gathering power. AI or artificial intelligence in spectral analysis can also be used in order to speed up processing of large data sets. So advancements in possibilities for significant discovery include the probing the formation of the earliest stars and galaxies, as well as conducting detailed analysis of exoplanet atmosphere to assess their habitability and composition. So any question, please?
Okay, Aman, go ahead with your question.
Okay, I just have 2 points. The first one is, what is the difference between a particle and a wave? And how would you go about when you address anomalies, like anomalies that don't like configure to the laws of physics? How would you attempt those or interact with those, since your job is to observe? Yeah, those are my 2 points.
Did you get the
Okay.
question, Shuge?
I
I'm not sure
didn't
if I got the first one. Aman, would you please repeat the first question?
The first question is, what is the difference between a wave and a particle?
Okay.
And the second one is about anomalies, how you deal with anomalies, how you observe or react to anomalies. Yeah.
Okay. You said the difference between a wave and particle. That's the first question.
Yes.
Wave and particle refers to dual nature of light and matters in physics, known as wave-particle duality. So wave nature, light and particles like electrons behave like waves in certain experiments. They can show properties such as interference and diffraction. For example, you have light passing through a double slit, which creates an interference pattern. For particles, light and particles also behave like discrete packets of light called photons of particles. For example, you have experiments like photoelectric effect. Photons striking silicon in a CCD create electron hole pairs. These are examples of particles too. So that's for the first question, the difference between the wave and the particle.
Yeah, the second
Then
question. Oh, yes.
What's the second question?
The second question is, how would you like deal with anomalies, like things that you observe in space that don't like confide to the laws of physics and like don't follow those rules, but they're there and the anomalies. So how would you observe of anomalies and record data on anomalies?
Okay, you said how to deal with anomalies that occur in physics, right?
In space, observable space.
Okay, let me, Shoge, if you want to answer it, okay, you go ahead. Otherwise,
Okay,
I can come
continue.
in there a little bit.
Okay, no problem.
Okay, if you have a spectra, then during the reduction of the spectra, you already showed you, like the then you have to remove cosmic rays. Cosmic rays, we assume, come from space, and this interfere with what actually you are observing from the star. So during the reduction process of the spectra, you remove these cosmic rays, and then you'll be able to have real signals from the star. Maybe I show something briefly. I will share screen and show briefly a physical relation of this red shift and blue shift, and also how we see spectra in real time or real. So if you look at this, can you see my screen?
Yes.
Yes, sir.
Okay. So if you look at this, I want to compare, maybe I have an eclipsing binary system where you have two systems revolving around a common center. Then if you look at this, in the first instance, where if you follow these tangential lines, if you look at this, you notice that this observer sees a line coming from this at the same time, and then you see them this way, coinciding at a particular point. Then, but as they keep revolving around that common center, at some point, this B, particle B, is moving away from the observer, while particle A is moving towards the observer. In that case, particle B is redshifted and particle B is blue shifted. This idea of blue shifting or red shifting is just a change in the energy of this thing, because if you are red shifted, you are moving towards the longer wavelength. Yeah, so you are moving towards the infrared. The other one is moving towards the blue parts, which is in a larger energy, a higher energy. So, and if you come to this place again, when the line of sight, when the motion coincides, you see this at this particular point. So by measuring this shift, you'll be able to estimate what we call the radial velocity, which previous presenters already told you. And using this radial velocity, you can fit the spectra of this star. This is a radial velocity fit, example of a radial velocity fit of a star, for instance. And this one shows the primary component of that star, and this shows the secondary component of that star. Then if you move a little further into this, you see a spectral line in terms of this. What I showed here is just, this is not actually meant for this workshop, but it is what it was one of the talk I presented somewhere. So if you look at this, you have a cross section of a spectra showing a H beta line and silicon triplet lines. So this thing shows you that type of absorption. In a spectra, the absorption lines are seen as these lines like eclipses. In assuming you are dealing with photometry, you see it like eclipses. If you have emission, instead of having this type of shape, it will be going up in upward direction instead of absorption lines this way. So when you see spectra plotted in terms of this wavelengths and the normalized flux, and you extract the RVs through this spectra by comparing this observed spectra with some synthetic spectra, then you can get the RVs, and then you fit it and get the orbital parameters of that system. Then using this spectra again with some synthetic spectra, you can also cross-correlate them and get the effective temperature, the log G, or the rotational, or the V sin I, which tells you more about the internal rotation of the star. So I think I wouldn't go for that, but I just wanted to show you some of these pictures to give you a clear perception of what a spectra is and how you see maybe RVs or measure RVs from a spectra. Maybe we can take a few questions.
What did Dr. Shoje want to say? She said she wanted to address something about the question.
No,
You said?
I'm okay with his explanation.
Okay. Yes, I addressed the question.
Thank you, Christian, for the explanation you have added to that question. I think that resolves the problem of the anomaly he's talking about when you are seeing some anomalous effects in space. So I think with the spectral analysis, I think the anomaly can be resolved to some extent. So I think we have come a long way. Listen, continue.
Yes.
If there are questions.
Yeah. Yes, thank you very much. To just wrap up, the spectra I showed is a spectra that we've already removed all the anomalies. So it's already calibrated and we've removed all the necessary required anomaly. So, and it's already just spectra that you work on. So we thank the instructor, Dr. Shuge, for the talk. And we thank you all for your active participation. It has been a wonderful experience from day one till now. And by tomorrow, we'll still be meeting again at 11 a.m. Watts. And tomorrow, that will be the concluding session of this workshop. Remember that you also need to submit a questionnaire tomorrow. Maybe by 11, you'll be able to see the time there. It may run for some time anyway. But apart from submitting the questionnaire, you need to be present, participate during the session for some other closing announcements or remark. And by the end of the program, you will be given certificates. We'll let you know tomorrow the modalities for receiving those certificates. I have also observed that only few persons have submitted the assignment we gave on Tuesday. So you should try as much as you can to submit the assignment. You can upload it as a PDF, or you just type in the content directly into the space there. There is no word limit. You can write as few as you can or as much as you can. Thank you very much once again for your participation, and see you tomorrow.
Thank you, professors.
Thank you.